Welcome to MEI Mechanics. We're on the topic of mechanics basic principles, and this is video 1.1, quantities in mechanics. So one thing that's very important when we're dealing with quantities in mechanics is to make sure we're aware of what units are being used. Most of the time, certainly, we'll be using the System International, often referred to just as the metric system, but that's its proper name there. And for things like mass, distance and time, which are amongst the most common quantities that we're going to be dealing with, we'll usually use the kilogram to quantify mass, the meter for distance, and the second for time. Now, depending on how large the quantities are that we're dealing with, and that'll depend on the type of problem, the type of situation that we're trying to model or calculate, we might decide to work in grams if we're dealing with relatively light things. So you need to know, of course, that 1,000 grams is 1 kilogram. If we're dealing with longer distances, we might switch to using kilometers, for example, when a kilometer is, of course, 1,000 meters. And a very handy little conversion to use if you're dealing with hours, that 1 hour, because it's 60 minutes and a minute is itself 60 seconds, 60 times 60 is 3,600, so 1 hour is 3,600 seconds. And another thing to be aware of all the time when you're doing mechanics is the distinction between scalar and vector quantities. So scalar quantities, they're the simpler of the two. They just have a magnitude or a size. So they'll just be a number. Okay, so things like mass, distance, speed, time, they are all scalar quantities. They'll just be a single number plus a unit that will give you that quantity. Vector quantities are a bit more complicated than that. They include the scalar quantity, which is the magnitude, but they also have a direction. Alright, so you might talk about travelling 3 meters north, for example. That would be a vector quantity because you've quoted a direction as well as a size. So the sort of quantities that we describe with vectors are displacement. Now displacement is like the vector equivalent of distance. Velocity, which is the vector equivalent of speed. Acceleration. Acceleration is a funny one because in some ways it could be used as a scalar quantity, but usually we're thinking of acceleration as a vector quantity. And force as well. Force is a vector quantity. So, for example, if you ever notice in a car it has a speedometer, that tells you the speed. It doesn't tell you what direction you're travelling in. So that's just measuring the speed, so that's giving you a scalar quantity. If you've ever worn a pedometer, a lot of phones have these built in, and if you ever look, it'll tell you how far you've walked or how many steps you've done. And again, that will tell you how far you've travelled, but it doesn't tell you what direction you've gone in, and it doesn't tell you where you are. So it's just measuring a distance, it's not measuring a displacement. And then when we're talking about vector quantities, then we're always describing them with both a size and a direction. So this is something that you'll meet more as we go through the course, but if you throw a ball up into the air, throughout its whole path in the air, it's accelerating. And that means its velocity is changing, but the direction which it's accelerating is always downwards, and that's due to gravity. So we're quoting a direction there as well as a size. In a game of tug of war, for example, there'll be two teams both applying forces to a rope, but the forces from one team are acting in opposite direction to the forces from the other team. So forces involve directions as well as sizes. So you need to make sure all the time when you're dealing with a mechanical problem or a question that you're aware of the quantities that are stated and that you're using the appropriate vocabulary when you're talking about these. You've got some choice often that you could sort of describe the same thing using vector quantities or scalar quantities as long as you're clear in what you're saying. So for example, if we've got an object that's moving backwards in some sense by 5 meters, so we've defined a forward direction and we find that something's moved backwards, we might say that the displacement was minus 5 meters. Alright, but we might just as well say that the object has moved a distance of 5 meters, as long as we then also say the direction backwards. So the distance of 5 meters by itself is a scalar, but then when we say distance of 5 meters backwards, that's now a vector, which is equivalent to this displacement of minus 5 meters. Alright, so as long as you're careful in what you're saying, then both of those things would be fine. So here's a simple example of this idea. You might want to just pause your video for a moment here and have a little read of this and see if you could maybe jot something down describing the journey, and also think about this question here. Is there a problem? Is there any problem with this graph? Alright, so hopefully you've had a bit of time to think about this. Maybe you've jotted down a few things about what's happened on this journey. In terms of the details of the description, we'll talk about that in a moment. But as for there maybe being a problem, well, there is a slight problem here. It's with this, well, two things. This labelling of this axis just as distance, and in particular this section of the journey. So clearly what's happening there is that she's travelling backwards. She's getting closer. Maybe she's gone back to meet a friend or something and then carried on. But the problem is, do we think this word distance is giving us the distance that she currently is from the start of the path, or is it the distance that she's walked? Alright, because if it was the distance that she's walked, well, it would never make any sense for this thing to get less. Alright, so if she's got carrying a pedometer that's measuring her steps, obviously even in this section of the journey that thing would still be increasing. So her distance travelled would still be increasing here, but the distance from home, or the distance along the path, that's decreasing. So it's important when you're labelling a graph and when you're reading a question or you're describing something that you make that distinction clear. So let's look at the details of this. So in the first 50 seconds we can see that something happens, something changes after 50 seconds, but in that first 50 seconds the distance that has been travelled is 100 meters, isn't it? Another thing we should probably say, of course, as well as this distinction between distance travelled and distance from home, is that before we changed what was on that axis, it just said distance, and we hadn't quoted the unit. So it is important, even though we'll be using meters more often than anything else, even when we're using meters we should always state that unit. So it's 100 meters. And the displacement is the same, because that's in the positive direction, that's 100 meters. What's the speed? Well, speed, or the average speed for a journey, is always the distance travelled divided by the time taken. So that is a speed of 100 divided by 50, so that is 2, and then we need units of meters per second, and what you'll see is that's normally written as m and then s to the power of minus 1. If you think about sort of indices, a power of minus 1 is the same as dividing, so we're dividing a distance in meters by a time in seconds. And the velocity, again, if we've defined this direction to be positive, then we can just say that also the velocity is 2 meters per second. Okay, then in 100 seconds, or after 100 seconds, the distance, well, okay, so the distance from home is really the displacement, so we can definitely say that the displacement is 160 meters. So if we follow the journey thinking about distance travelled, in this section she travels 100 meters. This section she's travelling a distance of 60 meters. So at that point she's gone a total of 160 meters. And then this section of the journey she's travelling a further 120 meters. So that means she's done a total of 280 meters. Okay, so the average speed, well, when you're dealing with average speed, obviously here the speed, even though she's travelling backwards, the speed is positive. Alright, speed is always positive. So in order to take account of that, what we need is to think about the distance travelled divided by the time taken to get to that 100 seconds. So that's going to be 280 divided by 100, so that's 2.8 meters per second. But the average velocity, well, velocity is a vector. Alright, so in this section of the journey, she's going to be travelling backwards, so she'll have a negative velocity. So in order to get the average velocity for the journey, what we do is we take the displacement. Alright, so we do the displacement divided by the time, so that gives us 1.6 meters per second. So here's another example. Again, if you'd like to pause your video for a moment, have a good look at this. Have a look at this displacement time graph with the car and the motorcycle both represented there, and decide what is happening. What comparisons can you make between the journey for the car and the journey for the motorbike? Alright, so if you've had a little think about that, a few things just in sort of vague hand-waving terms to begin with, we can see that firstly we can see that the car has started 10 meters ahead of the motorbike, so the car's had a head start in a sense. But the car's travelling at a constant speed all the time, whereas the motorbike, well, if we think about the speed as related to the steepness of the graph, well, this graph for the motorbike is getting steeper all the time. So that means its speed is increasing, which means that it's accelerating. And because it's accelerating, even though it starts off slower than the car, you can see that if you compare the steepness of those lines, starting off slower than the car, it's and it's starting behind the car, because its speed is increasing and increasing. Eventually, it's going faster than the car. Eventually, it catches up with the car and overtakes. Alright, if we want to think about that in more detail, think about that with some numbers, we could firstly consider the car. And if we look closely at this, what we see is that every second the car is moving forward by another 10 meters. Alright, so it's gaining 10 meters of displacement every second, and so that means that its speed is 10 meters per second. For the motorbike, if we look carefully at that, we see what's happening is that in the first second it's moving forward by 5 meters, in the second second it's moving by 10, in the third second it's moving by 15, and so on. So for each of those little 1 second sections, we can see that its average speed is going from 5 to 10 to 15 to 20. So its average speed is increasing by 5 meters per second every second. Alright, so what we do is now we're talking now about acceleration. So that's something which is a speed which is measured in meters per second already, and that's changing, and we think, well, how much does that change every second? So we need to think about this in terms of a unit as meters per second per second. So we'll say 5 meters per second, or the neatest way of writing that is to say 5 and then m s to the power of minus 2. Again, thinking about rules of indices, power of minus 2 is the same as dividing by the square of something. In other words, the same as dividing by that thing twice. So that was just a very quick introduction to the use of quantities in mechanics, and that concludes video 1.1. The next video will be 1.2, where we're going to look at modelling.